So before we start graphing, we want to talk about tangents at the pole. And once we're done talking about tangents at the pole, we're going to look at graphing examples 7 and finding its tangents at the pole, and then graphing example 8. Now, a tangent at the pole is a line that's tangent to the graph of your function r at a certain angle. So we say that if r is a function of theta, and you plug in some angle into r and it equals 0, but you plug in that same angle into r prime and it doesn't equal 0, then theta equals that angle is a tangent at the pole for r. So if r is equal to 0 at alpha and r prime doesn't equal 0 at alpha, then theta equals alpha is a tangent at the pole. Now things like roses, lemniscates, and circles will have tangents at the pole, but cardioids and limosons will not. Now the other thing I want to talk about is the number of tangents at the pole. Now if you remember what I just said, I said that circles, lemniscates, and roses are going to have tangents at the pole. So for a circle, really we're looking at r equals plus or minus 2a cosine of theta, and r equals plus or minus 2a sine of theta. Lemniscates, r squared equals a squared, and then it's cosine of 2 theta, and here r squared equals a squared, and then sine of 2 theta. And then roses is r equals a cosine of n theta, and here r equals a sine of n theta. These are the kinds of things that are going to have tangents at the pole. Now the number of tangents at the pole is the same as the number multiplying theta. Notice here that theta is not being multiplied by anything other than 1, so these will have 1 tangent at the pole. These are multiplied by 2, these will have 2 tangents at the pole. These are multiplied by n, so they're going to have n tangents at the pole. So that coefficient of theta is going to help you determine how many tangents at the pole you will have. For 7, it says to sketch the graph of the polar equation and then find the tangents at the pole, if any. Well, notice I have 2 in front of theta, so I know that I'm going to have 2 tangents at the pole here for my answer. And I'm going to go ahead and start by finding the tangents at the pole since we're talking about it, and then I'm going to graph this guy. So how do you find tangents at the pole? It has to be places where the function is equal to 0 and the derivative does not equal 0. And the first thing I'm going to do is set the function, the given function, equal to 0. So for these tangents at the pole, I have to start by setting the function, in this case 3, sine of 2 theta equal to 0. Solving for theta, I divide by 3, and then the sine of 2 theta is equal to 0. Now I need to figure out where in the heck does the sine equal 0. Bring down my 2 theta. Well, the sine is equal to 0 at 0 and at pi and at 2 pi and at 3 pi, and I can keep going, but I know that I have a 2, so I really only needed to list the first 2 because I should only have 2 answers, but I'm going to list a few to show you why you only have 2 answers. So to solve for theta, I divide by 2, so I'm dividing everything by 2 here. And theta would equal, well, 0 divided by 2 is 0. Pi divided by 2 is just pi over 2. 2 pi divided by 2 is pi, and 3 pi over 2. Now, let me show you why it's really only the first 2 answers. We do need to check it, but we'll talk about that in a second. Well, this is the line theta equals 0. If I talk about the line theta equals pi, well, it's the exact same line. This is the line theta equals pi. So I'm not going to say the same thing twice, so that's why I only take the first one. For the other one, this is the line theta equals pi over 2. Well, the line theta equals 3 pi over 2 is the exact same line. So I don't need to go more than 2 out because they're going to start repeating each other. So that's why your tangents at the pole match the number multiplying theta. But I need to make sure that these are tangents at the pole. So remember, tangents at the pole happen where r is equal to 0, but where r prime does not equal 0. So I have to find r prime and then make sure that 0 and pi over 2 don't make that guy 0. R is equal to 3 sine of 2 theta. What is your derivative? Well, r prime there would equal the derivative here, so don't forget about the chain rule, so you're multiplying by 2. So that's going to be 6 cosine of 2 theta. So now what is r prime of 0? If I plug in a 0, well, I get 6 times the cosine of 0, which is 6, which is perfect because I just cannot be 0. 6 is not 0. What about r prime of pi over 2? Well, that's going to be 6 times the cosine of 2 times pi over 2, which is pi, and that's negative 6, which is perfect because I just needed to not be equal to 0, and that was not equal to 0. Therefore, I know that the tangents at the pole here happen at theta equals 0 and at theta equal pi over 2. But now I want to sketch the graph because that was part of what I needed to do. So I need to sketch the graph of the polar equation. Well, I need to figure out what it is. Well, I have all these listed here. But let's pretend that I didn't have them listed. You can always check your calculator first to figure out what this looks like. So if I go to my y equals and I plug in what I'm given here, which is 3 sine of 2 theta, I realize that I'm looking at a rose that has 4 petals. So I have a rose that has 4 petals. This I know is going to be a rose. So how do I graph it? Again, if I put this down here, r equals 3 sine of 2 theta, and I know it's a rose. This tells me how far I move away from the pole. So I know I have to move out 3 units from the pole. It's a rose. Since this is an even number multiplying theta, I know that that means that I'm going to have, for my number of petals, 2n. In that case, this is going to be 4. So I have 4 petals, and I know I need to move out 3 units from the pole. I also know that I have sine, so I need to know where do I put my first petal and the spacing for the next petal. For sine, we said that our first petal is always going to be at 90 degrees divided by n. N is 2, so my first petal is at 45 degrees. My next petal is 360 degrees divided by the number of petals. Well, how many petals do I have? 4. So my next petal is 90 degrees away. If I were to graph all that, and I know I need to move out to 3, so I'm going to change the value. I'm going to make each one of these tick marks be half a unit. So that's going to be 1 unit away from the pole, 2 units, 3 units, and I'm just going to make those darker for each one of these. My first petal is at 45 degrees. Well, this is 45 degrees, so I know at 45 degrees I need to be 3 units away from the pole, so right here. My next petal is going to be 90 degrees away from that, so that's going to be at 135 degrees. So here at 135 degrees, I'm going to draw my next petal. I have 4 of these, so 90 degrees past that is 225 degrees. So draw your next petal. And I'm just drawing the point for that next petal, and then the next one's going to be at 315 degrees because that's 90 degrees away. So there's that point. So then draw in your petals. And there we go. That's the graph of 3 sine of 2 theta. The last example is just asking us to sketch the graph of the polar equation. So I have r is equal to 3 times 1 minus the cosine of theta. Well, that looks strange, so let's go ahead and just distribute my 3 here. That tells me that r is equal to 3 minus 3 cosine of theta. Well, what is that? Well, when these numbers are exactly the same, I know that that's going to be a cardioid. And remember, those cardioids look like hearts. For cardioids, limesons, and circles, I usually use a table of values to graph my function. Now this is cosine. Whenever you have cosine, just like we mentioned on the page above, we're going to choose angles from 0 to pi because we're symmetric with respect to the x-axis. For sine, we wouldn't use those angles. We'd use the angles from negative pi over 2 to positive pi over 2 because sine is symmetric with the y-axis. So since I have cosine, when I'm making my table of values, I'm just going to choose angles between 0 and pi. And I'm not going to choose every angle between 0 and pi. I'm just going to choose angles where the cosine has a rational answer, so nothing where it ends up with a square root. So I'm going to make my table of values here. Between 0 and pi, I'm going to choose the angle 0. And then pi over 3 because I know the cosine of pi over 3 is a half. I'm not going to choose pi over 6 because that's square root of 3 over 2 and that's a radical. I don't want to deal with it. Nor will I choose pi over 4 because again, root 2 over 2, radical, I don't need it. I'm going to choose the angle of pi over 2, 2 pi over 3, and then pi. So I'm just going to choose these values. And again, I'm choosing these angles because the cosine is either a rational number or a fraction or an integer at each one of these. So now I need to find the value of r. So I'm plugging things into this guy. So grab the calculator, plug those things in. Now I'm plugging in radians, so make sure your calculator is in radian mode. My calculator is in radian mode. So I'm going to do 3 minus 3 times the cosine of 0, which is 0. And then I'm going to do 3 minus 3 times the cosine of pi over 3, and I'm going to write in the values at the end. That's going to be 1.5. 3 minus 3 times the cosine of pi over 2 gives you 3. 3 minus 3 times the cosine of 2 pi over 3 is going to be 4.5. And then finally, 3 minus 3 times the cosine of pi is 6. So we have 0, 1.5, 3, 4.5, and 6. So let's draw all those points. So I have the point 0, 0, which is here. Again, I'm going to make it where each one of these tick marks is half a unit. So this is 1 unit, 2 units, 3, 4, 5, 6, and I'm going to darken everything here as well. The point 0, 0, angle of 0, 0 units away from the pole, is right there. The point 1.5 pi over 3, first go to the angle of pi over 3, and then go 1.5 units away from the pole. The point 3 pi over 2, go to an angle of pi over 2 and go 3 units away from the pole. 4.5, 2 pi over 3, go to an angle of 2 pi over 3, and then move 4.5 units away from the pole. And finally, 6 pi, go to an angle of pi, and move 6 units away from the pole. If I were to connect those dots, I'd have half of my cardioid. I'm missing the other half. Remember, this is symmetric with respect to the x-axis, so I get to reflect all these points on the other side of the x-axis. So if I take this point here and I reflect it on the other side of the x-axis, it's going to be right here. If I take this point and I reflect it on the other side of the x-axis, it's going to be right here. And if I take this point and I reflect it on the other side of the x-axis, it's going to be right here. So now let's finish graphing our cardioid by connecting the other dots. And there we go. That's the graph of 3 times 1 minus the cosine of theta. Now just so that you know, since we didn't have an example of it, if this were r equals 3 minus 3 sine of theta, the angles that I would have chosen to graph this, since it's sine, and you go from angles between negative pi over 2 to positive pi over 2, so you can have half of the side and you reflect to the other side of your y-axis, would be negative pi over 2, negative pi over 6, 0, positive pi over 6, and pi over 2. So if it's sine, these are the angles that you would choose in order to graph. That's it for polar coordinates and polar graphs.